Hello, everyone. I'm glad you're interested in learning about knowledge graphs using NetworkX and RDF. And this video is focused on exactly that. In fact, it provides you a nice overview of RDF, and then we'll jump into code to look at the key differences between NetworkX and RDF. And if that's a focus, obviously, you're at the right place. And it tells me that you're interested in knowledge graphs in general. So I recommend you to jump back to the last couple of videos to learn about knowledge graphs using NetworkX in the last video and what knowledge graphs are in general, right? So, and also the next couple of videos at least are going to be focused on this specific topic where we create a recommender engine. So if you want to be notified, obviously hit the subscribe button. So pause right now, hit the subscribe button, and while you're there, try to find the little thanks button if you're feeling extra generous. Okay, so before delaying any further, this is going to be quite a few, for my standard, quite a few PowerPoint slides, meaning I guess 8, 9, 10 slides. And there is a reason for that, because of course we need to understand the background. And then at the end, we are going to jump into Google Colab to explore both NetworkX and RDF for a simple scenario. And then in the next video, we're going to pick up actually with a specific example of creating a recommender engine. Okay, I think I talked for too long. Let's go ahead and start learning about knowledge graphs and NetworkX and RDF primarily. So first of all, what are knowledge graphs? Please watch my video from the last, video number 353 and 354, the last couple of ones. But just a quick short summary of knowledge graph is it allows you to represent, or knowledge graph is a representation of the concepts, certain concepts. And you define those and you represent those as nodes and edges. Edges are nothing but the relationship between these nodes. And on the screen, you see Python basics. For example, if you are looking to map out the Python learning journey, you have Python basics. And after the basics, you probably want to learn about data structures and then advanced Python and so on, right? So the basics is connected to data structures. In this example, basics is a prerequisite before continuing to data structures. And what is the weight? Like weight 1.0, you must actually do this, right? The weight is, it can be, obviously it depends on the scenario. Okay, so this is more than what I wanted to talk about knowledge graphs. Again, the last couple of videos are dedicated to that, but knowledge graphs are represented. You can represent them using NetworkX, right? I mean, in Python, obviously we covered that in the last video, but RDF, Resource Description Framework, is something that you should know of, whether you end up using it or not, if you're dealing with knowledge graphs. And it's basically a standard. Think of other standards like XML, for example. You probably heard of XML files, right? So someone defined how these standards need to be for XML. When I say that someone, that's the World Wide Web Consortium. So they defined this, and they're the same entity who defined the standards for RDF. I believe that dates back to late 1990s, and when actually got formalized was the early 2000s and modified again later, I believe later that decade or early 2012-ish or time frame. But history doesn't matter. These are the ones who kind of defined the standard. So think of RDF as a standard. And why is that important? Well, if you want to exchange it, of course, it's free and open standard. It allows for these directed graphs and with labeled edges, right? So this is what knowledge graph is. And you can actually draw multiple edges between the same nodes if you have different labels, right? So for example, if you have Python and if you have data structures, there was like one edge or one connection, which is, hey, this is a prerequisite. But then there can be another edge, another connection between the same nodes, but that means something else. So you can actually, anyway, I don't want to get into a rabbit hole of thinking of various hypothetical scenarios, but basically RDF actually allows you to do these type of things. Why? Because if you have different labels, then for each edge, then it is possible to actually do multiple edges. So it's not designed, it doesn't force you to do that, but its design allows you. for such scenarios. I don't know why I put that at high right there, but basically RDF requires something called URIs to name the edges. I thought I have written somewhere, why do you even need RDF? It's basically, it makes your life easy when you're exchanging these with someone else. When you have a graph coming from one source, you have another graph coming from another source, and you want to work with them together, then you need to make sure all the nodes are unique from each of these graphs. Otherwise, you kind of mix them, and you have to do a lot of pre-processing before working with them. So it makes interoperability easy. So that's the whole point of RDF. Okay, I should have put that as a bulleted item. Apologies, but let's continue. So with that information, how do you put unique nodes? How do you name the nodes unique? Like I called it Python basics. Obviously, in a different graph, it's also probably something called Python basics that may be meaning something else. Like when you merge, when you try to work with multiple graphs, how do you make sure that, hey, this is unique? So this is where URI comes in. So it requires these URIs to name your nodes and edges. I'll talk about URI in a minute, but RDF itself, the way you describe, you define these nodes, or these graphs are by actually using these triplets. Whenever I use the term triplet, it basically means it must have a subject, a predicate, and an object. Yeah. So basically, it's like Python basics is a prerequisite of data structures. A subject, a predicate, and an object. Python basics. And what does the edge mean? The connector is a prerequisite of, in plain English. And then the next node is data structures, right? So this is your subject, your predicate, and objects. So this is how RDF defines. Basically, you are defining it in this framework. And I'll also talk a little bit about namespaces, which is part of the RDFlib in Python, one of the libraries. And it kind of helps you abstract this a little bit. Again, right now it may not make sense, but after a couple of slides, hopefully it should start make sense to you. Now, let's understand the URI. I mentioned about URI right here, right? So the fourth bullet point is about RDF requires URI. What does URI mean? I mean, URI is like the most common URI that you know of is URL, right? A website URL. That's a form of URI. I in this case is identifier, right? So they are used to uniquely identify nodes and edges. So why do you even need to use these URIs? Like I mentioned, to avoid the naming conflicts when you're working with different graphs that potentially come from multiple sources. Now, why does it look like a URL? I didn't even show you what a URI is. For example, a URI can be HTTP www.example.org. I mean, it looks like a URL, and for a good reason. It looks like a URL because URL is a form of URI. I think in the next screen, I'll show you what a URI looks like. Now, the question is, okay, if it looks like a URL, can you use your domain name? Of course, you can use your homepage URL. But the whole point here is the URI, it doesn't have to lead to a live page. It shouldn't, it doesn't mean mydomain.com should exist. It just needs to be unique. So for a URL, you know how when you type a URL, it goes to a specific page. It's going to that specific page because that URL in the entire world is unique to that specific page. That's why it's pointing to that page. Similarly, a URI points to your specific node or an edge, the full URI. It doesn't mean someone clicks there and then comes to your node. It just represents it. That's a notation. Okay. Now, basically, look at this. This hopefully should clear any confusion. So the node right here, Python basics, for example, is written as http example.org Python tutorials/basics. This is the unique URI. Probably not as unique because example.org is, anyone can have that, right? If I have my own domain, I don't know, digitalsrini.com, and if I have http digitalsrini.com/Python tutorials/basics, that would be unique. And then when you get to use it and you get a different graph from some other source, then you end up with unique nodes and unique edges right there. So again, just to summarize this, they look like URL because URL is a subset of URI. These, when you click on this, they don't need to go to a specific page. They can, if you want. On that page, you can say, hey, this URI is, it represents a node, blah, 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 whatever it is. You can have a website, but that doesn't mean you should have one. Yeah, you can just define anything. Okay, moving on. So I think I already mentioned, it doesn't have to be a valid URL. That's the whole point. Now, when exchanging graphs, obviously using URI ensures that your identifiers remain unique. I find myself repeating this 3-4 times because initially when I started learning about this concept confused the hell out of me. I'm like, what is this? This is like URL. Why should I put this? Why can't I put node and all that? But obviously think of interoperability. That's all. That's the whole point. It comes down to that. Okay, now local URIs, like for example, when you put example.org, right? If I'm using it on my own system, I'm not sharing with someone else or whoever, I don't care. I'll just put HTTP, I don't care.org, whatever, it doesn't matter. But these are locally scoped, right? So and they're not intended for global use and for being unique. But if you're actually sharing these, then of course you have to think of the global use. For shared systems, like I said, like for global use, unique URIs would obviously avoid any conflict with other graphs that you're working with. Okay, so just to make more sense out of this, so here is a typical knowledge graph, right? Like you have multiple nodes, like Python basics going to data types, and from data types, if you want to work with image processing, you may want to jump into image basics and take this bottom path and so on. So this is a very simple knowledge graph that you're seeing here. How do you represent this in RDF? This is a non-RDF graph, a typical graph that you would see. In RDF, it's exactly the same terminology, except you are putting example.org. You are putting an URI in these nodes and edges in the form of URI. Now you can see here the tutorials/basics, example.org relationships /teaches data types. So the basics, and then the next step is teaches data types, and then the next node is data types, and then the next one is teaches image basics, and so on. So you can create, I just made this up, but again, this can be anything. The edge must make some meaning, make some sense. Why? Because these are knowledge graphs. Knowledge graphs, by definition, they have semantic meaning. They carry semantic meaning from one node to the other, and RDF is designed to do that. Subject, predicate, object. Think of the triplet. It means something in plain English. Okay, so now that hopefully you're convinced about URIs, I just want to make a quick note about namespaces in RDFlib. I should have said RDFlib library here. A namespace is a way to group all these related terms. For example, if I go back, every one of these, each one of these, they have like http/example.org. Right? So instead of typing this in your code, you just say, hey, it's almost like assigning it to a variable, right? So you just say, hey, ex equals to namespace, whatever the namespace you want it to be in. And then when you define, for example, Python basics, you can just say ex.python basics. So this is again basics of how you would define a RDF based nodes and edges in Python. That's pretty much it when working with RDFlib library. Okay, so with that gone, now let's explore these two libraries to define a few scenarios. Let's go through a few scenarios, and I assume you're a bit more familiar with NetworkX, especially if you watched my previous video. So we'll compare NetworkX and RDFlib to see how things look slightly different. Now, creating nodes in NetworkX is pretty straightforward. Once you define your graph, you just do @_node or add_nodes when you're actually reading multiple nodes from a dictionary or so. So let's focus on a single node. Okay, @_node, and in this node is labeled Python basics, and the attributes of these nodes are the difficulty equals to beginner, and the description is basic Python concepts. So these two are the attributes. The name is Python basics. How would you do this in RDFlib? First, you define a namespace that you want to attach, right? So here I called it EX, and then very similarly, you define a graph using RDFlib, and then you .add, and when you're adding it, you're adding the Python basics as your name, and you have the type and the topic, right? So these two. Again, we'll see more examples once we get into the code in a few minutes actually. So obviously the key difference here is NetworkX uses a simple identifier, so you can define like a dictionary of your names and the attributes, and you can just add all the nodes in an easy way. Here it requires URI based identifier, so that's the first key difference that you see right away. Now, how do you create relationships, which means edges? In NetworkX, you basically add an edge, right? So g dot add underscore edge or add underscore edges if you're doing multiple. And again, edge is connecting two things, right? So here it's connecting two nodes, Python basics and data structures. And they're connected and with a weight of 1.0. These are the attributes I decided to add to the edge. You can add other attributes, but in RDFlib, exactly similar. You probably saw this coming. Your subject, object, predicate, right? So Python basics and data structures are these two ends, two nodes, and you're connecting them with an edge, and I just call the edge teaches, okay? So Python basics, maybe the edge should be appropriately named as prerequisite. Python basics is a prerequisite of data structures. That would have made much better sense than teaches, okay? When I originally wrote this, I'm like, okay, Python basics, then it teaches how you can interpret, understand data structures or whatever was going on in my mind, but hopefully you got the point. So the edges here, you have subject, predicate, and object as the triplets. So this is how you add your edges. So again, represents with triplets, with subjects, predicates, and objects. And now let's add metadata. So in NetworkX, again, the metadata is just added to your nodes or edges. We saw this earlier when I add a node. You have difficulty as beginner and description. You can add a description, you can add weight, you can add other aspects, right? It can have many attributes as part of your metadata. So here description is basic Python concepts. If you want to do the same in RDFlib, again, you're adding Python basics and the difficulty and RDFlib literal. I'll talk about that when we get to code. Literal basically means this is not a URI. So it's not like example.org/beginner or something. So when you add this attribute, beginner, we are adding that as a literal, which is just a string literal. Yeah, again, which means it's not a URI. When you put ex dot, by default, you're saying that, hey, this is a URI and not a literal. So same here, you're adding another literal right there called Python basic concepts. So it takes a little time to wrap your head around the concept of RDF, and at least to me, who is a slow learner in a way. I'm a slow learner because I want to understand every little thing, before moving on to the next step. Otherwise, I get so freaking confused. Yeah, so let's move on to the next one and look at serialization. So this is something that I commonly do, like when I save my networks. What does serialization mean? It basically means, hey, I want to save these network into some other format, like where I'm converting this data into something that's not a graph. Okay, so you're saving a graph into something that's not a graph. Typically, you can think of this as saving your graph as a SQL database. Right, so then you're defining tables and you're defining different, names and so on. You're converting the graph nodes and edges into, different names and storing them as tables. So that's one way of serializing it. Now, Turtle, RDF, XML, GML, GraphML, these are many ways of actually serializing these graphs. And NetworkX, you can actually, there are certain formats that are designed for graph storage, like GML, GraphML, and Pickle. And RDFlib serialization, Turtle is I think at least the most common one that uses the semantic web standards to store these graphs. Again, Turtle allows you to store them as these triplets. So again, it comes down to basically saying g.serialize and graph.ttl, whatever the name you want to give. And of course, the format in this case is Turtle. And this allows you to just save it in that structure. And once you save it, later on, you can just load the serialized graph, and then you can start analyzing it. That's basically it. You don't have to serialize, by the way. You can store graphs, and there are many other formats to store. I just wanted to include this because I think in next example or so, where I intend to use at least not use, at least to demonstrate how you can serialize your graph, a NetworkX graph, into a SQL database and run some SQL queries on it if you're comfortable running queries in SQL. Which brings up to the topic of querying and running algorithms on the graphs. What's the point of building a graph? Because you want to find patterns, you want to analyze structures, you want to answer questions through some sort of a querying your graph. So to do that, querying and running algorithms are obviously essential, and NetworkX has built-in Python functions. I always work with NetworkX. That's why when I struggle sometimes with RDF terminology here, you probably can tell right away. It's not like I do that on a daily basis. It's just that I taught myself of what RDF is and everything. I did it. I occasionally, do that to make sure. Work with it to make sure I don't lose touch with it. But I'm not an expert on the RDF, as you probably can tell. That's why I switched back to my comfort zone of using NetworkX in the next couple of tutorials. Just as a side note. You may find much more. I haven't even looked at what other videos on RDF are there on YouTube. Maybe I should have. But if you really want to learn more about it, please go ahead and search for specific videos. But this should give you a good overview. Okay. RDF, if you want to query it, you require skills in SparkQL, which is, I think, kind of similar to SQL querying, but this is slightly different. It's a semantic web query language, so you need to learn a little bit on how to query it. Nowadays, with the help of ChatGPTs and stuff, you probably can ask questions and get some basic queries going on. But the problem with using language models is if you don't know anything, then they're useless, right? They'll give you something, you're like, oh, let me try this. You need to know the basics so that when it gives you wrong answer, you know that it's wrong answer and you can tweak it. Just a side note about using language models. No shame in using them as long as you know that, okay, what it's giving you is correct to the task that you're trying to perform, and you having enough skills to edit it or ask another question to the chat engine. Okay, I tend to go into these side rabbit holes for some reason. Okay, and I already mentioned about SQL. So NetworkX querying, it's very easy. As you see, once you define a graph, you can just go ahead and say, okay, so what is the shortest path? All you need to do is, hey, this is my NetworkX and x.shortest path. Apply that to the graph that I showed you, and then the starting node is A and the ending node is D, and give me the shortest path in the graph going from A to D. It's very easy, right? It makes sense. That's why I prefer this than any other approach. Centrality, for example, you have all this map. There are various ways of different types of centralities. Depending on what your goal is, they can indicate the importance, the relative importance of a specific node. And if you want to find that degree centrality, for example, it's just nx degree underscore centrality. I like this approach. I'm basically a physicist where the terms are based on some sort of a meaning, right? So if someone says a black hole, right? So it tells you it's something, it's a black hole. It looks dark. Light cannot get out of it, right? So the name means something. But if you go to like some geology, mineral naming, or biology, I don't even know how they name stuff. It's tough. You have to memorize stuff. Here, you don't have to memorize stuff. This is very similar to physics approach. Hey, what is the shortest path? Shortest underscore path. What is the degree of centrality? Degree underscore centrality. You'll see most of this approach in NetworkX, which makes it easy for you to learn. Again, if you are like me, who requires, things to make sense before proceeding to the next step. Okay. Now, RDF querying is, as you can see, it looks very similar to your SQL querying, where you actually obviously put your prefix to convert that into a URI, and then you're saying, hey, select ? Topic, where topic requires Python basics. Yeah. So this is a way. Again, this is something you need to learn if you plan on using RDF querying. Okay. Now, all good. All that explanation, which one should I use? I think I already mentioned about my preference. I always use NetworkX Because if you want to perform advanced graph computation, when I say always, I'm not talking about, oh, at work I go and I work with graphs. When I say always, I mean, I'm trying to find learning. I mean, I teach a bunch of kids on Python in my neighborhood. I'm like, how do I customize the learning path for a kid whose goal is to be, for example, a mechanical engineer, or whose goal is to be a physicist, or someone's goal is to be a biologist, right? I can kind of manually do that, but I have like, there are so many topics. How do you customize that? Then go ahead and use NetworkX and let it guide like what topic should come after what, and so on, and we can tweak it. So that's just a quick example I'm giving you. But yeah, so if your goal is to perform these graph computations, like finding the shortest path and finding the recommender engine, for example, for learning courses, then and also obviously to visualize the network, right? So we are humans, we like to visualize stuff. Then NetworkX can be very useful. For large graphs, very large scale graphs and large scale computation, look for alternatives like, for example, Neo4j. This is a commercial software. You obviously need to pay for this, and it lives up to its reputation. You pay for it for a reason. So it is designed to store graphs in its native format, and it's designed to allow you to work with these graphs. So Neo4j, if you're working with extremely large data, you may find that to be useful, especially once you try NetworkX and you find that to be a bottleneck. Now, use RDF, for example, if you want to store and query data with semantic meaning and ontologies, when you're defining all these ontologies for your new file format, for example, or share it with, exchanging it. When do you save stuff into XML? Right, when you have a TIFF file and you have XML with all the metadata about the TIFF file, you have an XML with it, right, with the TIFF file. So it's there. When you're exchanging that TIFF file with someone else, sometimes you can embed XML within TIFF file, right, to store the metadata. When you exchange it, they can open it and they get access to your metadata right away. So if that type of applications is what you're thinking of with your graphs, then of course RDF would be a good approach, because that's exactly what it's designed to do, interoperability. Now, that was a lot of talking from my side. Let's just go ahead and jump into our Google Colab to look at some Python code. Okay, so here it is. I am zoomed in a bit, otherwise I may need my glasses. I still probably need my glasses occasionally, but yeah, so let's go ahead and start. This is on Google Colab, so all of you can easily access it. And again, the link to this code is down in the description. Okay, so let's go ahead and start by installing the two libraries that we have been talking about, NetworkX and RDFlib. I hope you can read this. Let me zoom in further. So I can see it, my personal benefit. So let's go ahead and pip install NetworkX and RDFlib. It should be pretty quick. I mean, obviously Google Colab doesn't come with these two pre-installed. So there you go. Very quick, done. Now, there's a lot of text here. So again, we went through the presentation, so no point in reading that. But let's go through the first step here. So how do we define a graph in using NetworkX? And I'm also importing matplotlib like pyplot, so we can just plot and have a quick look at the graphs on the screen. So first thing, again, I covered parts of this in the last tutorial. The first approach one is using NetworkX, of course, and we are defining a directed graph. Digraph basically means directed graph, meaning it goes from Python basics to the next step, data structures, but not the other way around. You cannot go from data structures to the basics. So that's what a directed graph is, and then we define the nodes. You can define one node at a time, like I showed you in the PowerPoint presentation, or you can just define a dictionary. In this case, I'm defining the dictionary of topics that includes the node names, Python basics, data structures, advanced Python, and each topic has a couple of attributes associated with it, difficulty and description. These are the two, right? So I just defined a handful of nodes. Again, we'll look at more nodes in the next one, and even more nodes using natural language processing in the video after that. So now how do we add all of these? For each of these topics and metadata, go ahead and add node, g.add_node. We are unwrapping the metadata dictionary right there. So it's adding the topic and the metadata right next to it. So this is your nodes right there. And similarly, we need to define edges. So for relationships, I have, which is what our edges are. We have Python basics to data structure. So this is from, this is to, and the weight is 1.0 in my, you can add whatever you want. And then I'm adding like 1, 2, 3, 4 nodes only. So there is no multiple nodes branching and all that stuff. I just want to keep things simple. And these are the nodes. And again, go ahead and add edges, not just add edge, add edges from, and we are adding it from the dictionary, from this list of tuples called relationships. Okay, now that it's defined, now we need to find the shortest path. I already showed you the example as part of the PowerPoint presentation, but see how easy it is. Once you define that, all you need to do is import the shortest path method from your NetworkX library. And here we are querying, we are analyzing the graph that we stored as variable G. And the source is Python basics, target is bioimage analysis. You're going from Python basics to bioimage analysis, and we are going to it's going to extract shortest path. Let's go ahead and print the shortest path right there. Now, I want to visualize it, so I am just going to print it out. Again, typically I use Spring Layout. Maybe I'll make a video on different ways of different ways of actually visualizing, but Spring Layout is probably the most common one. So within NetworkX, I'm gonna assign the Spring Layout to a variable called POS, and then all I'm doing is draw the nodes and draw the edges using again within our NetworkX, and PyPlot is just in the background, and I'm just going to show that. So this is the plan. So we defined a graph and we are plotting it, and it should be pretty quick. And as you can see, it's going from, it looks like it's complicated right there. Oh, looks like we have the advanced Python is going to machine learning, and it's also going to bioimage analysis. Where is it? I have to check. I may have overlooked that. Advanced Python, advanced Python is going to machine learning. Advanced Python is also going to bioimage analysis. That's why you see the branch right there. So it's going from Python basics to data structures to advanced Python, and then branches out. By the way, if I run this again, it may lay out, you see how it changed the layout? So that's kind of random. So now it's going from Python basic. It's the same. It's just that graphs, there is no X and Y coordinate, right? It's all about connections. It's not like a plot. So every time you run it, it may show up in a random way, but the meaning doesn't change. So Python basics to data structures to advanced Python, and it's going to machine learning, one node, and the other one is going to bioimage analysis node. That is it. That is as simple as it is. Now, no wonder I work with NetworkX quite often. Okay, so if you look at RDFlib, we are importing the graph, very similar. And namespace is there to, I already explained what namespace is, and literal is just a string literal. And let's go ahead and, oh, why did I run? We should be going through the code. So I'm defining my graph. I'm initiating my graph right there. And to the graph, I'm going to add different components. First, before adding anything, I want to define my namespace as example.org. This is where you can define whatever you want. In this case, example.org. And now we want to add the same nodes as before. So I'm defining exactly the same dictionary as before: Python basics, difficulty beginner, description, Python basic concepts, and so on. This should be exactly the same. And add topics and metadata to RDF is the next step. Now what we're doing is, okay, so let's go through this. Each g.add call down here creates an RDF triplet. I should have said triplet here. Subject, predicate, and object. Right? So these are the three that we need. So you have topic URI, this is the subject, predicate, and object at the last one. And literal topic basically is, when we say literal, like right there. So machine learning with Python, for example, is not a URI, it's a literal. And that's what we are adding right there. So the metadata is added as literal. And these are URIs, like the node and the edge are both URIs. That's basically what's going on right there. And we are adding the nodes right here. Now, once the nodes are added, we need to define the edges. Edges are defined exactly the same way like we did earlier. Python basics, data structures, and 1.0 weight, and it's exactly the same thing. Now we need to add relationships. which means edges. And the weights, same thing. We have three things here, right? Python basics, data structures, like where the first node is, where the last node is, and what the weight is. So we are basically extracting those three from this list, and then we are adding them as source and target, right? So Python basics is the source, and this is the target, and we say, hey, this requires whatever the last thing is. And our weight is what we are adding as the predicate in these cases. Okay, and once the graph is defined, so here the graph is defined, right? You define nodes, you define edges, the graph is there. You need to query it. And here is the example query I showed you earlier using your SparkQL and prefix. And here we are basically saying Python basics requires what topic, basically, and Python basics weight. It's basically we are trying to extract the weight in this case for each of these relationships of the Python basics. I think we only have one relationship right there. And yeah, so we are basically here running the query. We defined the query over there, and we are running the query right here, basically, and printing it. So we already did that. So first thing, what we are printing is, what are we printing? I should have just separated the code, sorry about that. The first print statement is right there, waits for the topic. In fact, there's a reason why I printed this. Just a second, let's go back. Okay, so these are the namespaces topics, and for the topic we are adding these, we are adding relationships, querying it. Okay, so for weights, print. Okay, so apparently these print statements are directly coming from let's run this again. Okay, so basically you see the nodes right there. Okay, the nodes are example.org/Python basics, example.org/data structure. So these are all the URIs for the nodes. So these are the node names. And then we are printing, I probably have some printing statement. You probably are yelling at the screen saying, hey, you overlooked the print statement somewhere. Or it automatically prints the node names. But I don't want to waste your time by trying to find that little thing somewhere. Okay, so, but these are the nodes, as you can tell, the URIs for the nodes. And then the weights for the topics, when we queried it, there is only one weight for the thing that we queried. It says the weight is 1.0. And then at the end, I am actually serializing it using g.serialize format equals to turtle. And I'm not just saving this turtle, I'm just printing so you can see how it looks like once it's serialized. So you can see this is how it's actually saving after serializing it. So this is your RDF graph in turtle format, and it's telling you, hey, these are the prefix. When you go down and you see NS1, the prefix is basically example.org. So put example.org prefix before these. That's what it's saying. RDFS, this is the prefix for RDFS. So whatever, do I see RDFS right there? So when we define a label, it's going to put this prefix, and it's going to put like the RDFS right there. So this is basically it. This is how it's serialized. And now you can actually load the turtle format, the serialized format, and perform your queries. Okay, that is a lot. And I think this is probably it when it comes to RDF. In general, like I said, this is where the extent of my knowledge kind of goes through, because I haven't used RDF for something larger scale other than the core concepts. But I bet in the next one, you'll learn even more about actually practical aspects of NetworkX, where I plan on actually going through my own YouTube video tutorials list. I downloaded all the video titles and the description that I uploaded as part of YouTube, video description, and I captured that into an Excel sheet, and we are going to use that Excel sheet to kind of, build our knowledge graphs and all that stuff. So if that is of interest, and again, this is just a recommender engine for learning paths, like Python learning path, but you can use it for anything, your product development or something, right? So these are just concepts that I hope you are learning by watching these videos. I'll see you again in the next tutorial. Until then, please do not forget to hit the subscribe button. Thank you.